Hi everyone, welcome to the final video on this series of free vibration of multiple degree of freedom systems. We're going to keep on looking into the example of the house that we looked in the first three videos. So if you didn't watch any of the first three videos, I recommend you watching before watching this one. What we discussed was the dynamic equation of equilibrium in the coupled form. We talked about stiffness matrix and mass matrix, and then we started talking about something called the modal circular natural frequencies. We start talking about modes of vibration, and now we're going to basically go back into the beginning, do a full 360 and get the dynamic equations of equilibrium, but now written in the uncoupled form. So as a little recap, the coupled form of the equations just means that in our dynamic equations of equilibrium, the motion of the two masses is interfering with each other, and because of that, we didn't know how to calculate it. Now, the secret to unlock this coupled dynamic equation of equilibrium is a concept of modal analysis or modal superposition. If there's an important concept to understand, is this one, more than knowing how to calculate the numbers and how to do it by hand. Most of the softwares do this automatically, so it's important that you have the concepts very well established in your mind, in your brain, before you become an engineer, before you start designing structures on your own. So the concept of modal analysis is any vibration, structural or not structural, anything that is vibrating, the motion can be described as a sum of the individual contributions of each mode of vibration. So if we go back into the concept of our house, that we learned how to calculate phi1 and phi2, so the first mode of vibration and the second, what we're basically saying is that the motions of our bodies, so x1 and x2, so the motions of our degrees of freedom, is nothing more than a component from mode 1 plus a component from mode 2. So basically we're doing the superposition of the modes to get the displacements, okay? That's what we call modal analysis, and it's very important that at least this vague idea on how this works is very important that you have in the back of your mind. If we look into this in the context of our house, we're basically saying that the motion of the first floor and the motion of the second floor is nothing more than a contribution from the first mode of vibration plus a contribution from the second mode of vibration. And now there's a little thing that we don't know what it means, is this y1 of t and this y2 of t. What this basically means is the displacement of mode 1 and the displacement of mode 2. And note that this is dependent on time. So basically what we're going to do is try to track where is mode 1 with respect to time, and if we know where mode 1 is, when we multiply by the mode shape, then we know where the first mass is and where the second mass is. But this is not enough, because we also need to consider the contribution from mode 2. So what we're going to calculate with respect to time is the displacement of mode 2. Where is mode 2 at that particular point in time? If we can answer this question, to find the contribution of mode 2 to our motion of our degrees of freedom, we just need to multiply by the mode shapes, and when we add the two components, we finally get the correct answer, the accurate answer of the motion of our structure. If we look into this idea and try to write it in matrix form, this is the way it looks. So x being the displacement of our degrees of freedom, so x1 and x2, is nothing more than the modal matrix, and the modal matrix looks like this. It's just your mode shapes written as column vectors, and we times by the vector y, that's just y1 and y2, which is the displacement of the modes. Now, in summary, we could read this equation as the displacements of the masses, or if you want, the displacements of the degrees of freedom, is equal to a sum of the mode shapes times the displacement of the modes, where the mode shapes gives you the shape of the motion, while the displacement of the modes gives you a scale. And it's this scale that is dependent on time. This is fixed, always the same shape, but with respect to time, these displacements will be changed. So now looking into our example, phi1 and phi2 are given here on the side from previous videos. The motion of the first floor is 0.5659 times the displacement of first mode, minus 1.064 times the displacement of the second mode. And the same applies for y2 with the two components of 1.0. If we write this in matrix form, we get this shape, so it's modal matrix. So again, just the two vectors written as columns of our matrix times y1 of t and y2 of t. So this modal displacement vector, if you want to call it like that. So simply looking at this picture, we can understand that if we know where mode 1 is, let's say we calculate that at a particular time mode 1 is at 10, and we calculate that mode 2 is at 5. If we want to know where is the second mass, so where is the second floor, it's going to be 10 times 1 plus 5 times 1. So we know that this mass is at position 15. And if we want to know the first floor, right, we just do 10 times this quantity, so 5.649, plus 5 times minus 1.064. And if we do this combination, we can find the position of mass 1 in that specific point in time. So I hope this makes some sense at the moment. Now let's just look into some mathematics to try to wrap up why this works. So if we look at the dynamic equation of equilibrium in matrix form, and remember that this gives you the coupled equations, right? So that's not what we're interested in. So the first transformation we're going to do is replace x by the modal matrix times the modal displacements. So if we do that, we get to this equation. So we replace x double dash by matrix phi times y double dash, and then x by matrix phi times y. And the next step that we're going to do is pre-multiply everything by phi transpose, and we get to this equation that we're going to analyze a little bit better in the next slide. So now, what are we interested in calculating? We're interested in finding these two weird matrices of phi transpose times m times phi. If we remember that phi is just our modal matrix, so again, modes written as column vectors, and we're trying to do phi transpose m times phi. A little refresh on what transposing is. So if you get a matrix A, if you want to do the transpose, you just swap the two terms in the main diagonal. And if it's a 3 by 3 or a 4 by 4, you just mirror your matrix based on the main diagonal. So in this case, this is your transpose. So you can see that we swapped this value with this value, so we get here, and then we get times m and then times phi. So we could do this straight away and get the result out of this. But I don't want to show you this calculation straight away. I want to split this into smaller pieces. So instead of doing the entire matrix transpose times m times the entire modal matrix, I just want to focus on phi 1. So let's do phi 1 transpose times m times phi 1. If you remember, phi 1 is just 0.56491, so this is the transpose of this. And if we try to follow the calculations in this case, we get 0.5649 times 5, and then plus 0. Second component is 1 times 3. And then when we do this multiplication, we're going to do 0.5649 times 5 times 0.5649. So what we get is the squared of these two times 5, plus the square of 1 times 3. So funny enough, we get to a scalar. So if we do the first mode transpose times the mass matrix times the first mode, at the end of the day, we get a scalar. Now, we've done that, and if we do the same, but now for phi 2, we get another scalar, but now different, okay, now 8.66, which is okay, but look now what happens if we do the multiplication, but now the modes are not the same. So if we do phi 2 transpose m times phi 1, at the end we get 0. If you don't get 0 when you do this calculation, it's because of rounding errors, but in theory you should get 0. And if you do phi 1 transpose times m times phi 2, you also get 0. So in summary, what I'm trying to say is, if we try to do a mode of vibration times the mass matrix times another mode of vibration, this gives you a number if the two modes of vibration are the same. Only if n and m are the same number. And if they're not the same number, what we get is 0. And that's a very interesting property. If we now try to solve for this second term, so phi transpose k phi, what we're going to see is that it follows the same properties. If it's a mode times k times another mode, it only gives you a number if the modes are the same. And if the modes are different, you get 0. These are quite important properties of our modes of vibration. If we do one mode times the mass matrix times another mode, only gives you a number if we're talking about the same mode, and if the modes are different, you get 0. And this is also valid for the stiffness matrix. If it's one mode, stiffness matrix times another mode, only gives you a number if we're talking about the same mode. This is what we call the orthogonality condition of modes of vibration. Now, I'm not a mathematician to explain you very detailed what is the orthogonality condition, but I'll give you a metaphor so you can have it as a backup so you can remember what this means. Think about a force pushing a body, and the body has a displacement delta. The work done by this force on this displacement is force times delta times cosine of theta. What happens in the special case where the force and the displacement are orthogonal, or that means they have a 90-degree angle? In this particular case, because the cosine of 90 is 0, you get that the work is 0. So if the displacement and the force are orthogonal, that means that it wasn't this force that caused this displacement, right? The work done by this force in this displacement is 0. So the orthogonality condition of modes of vibration I interpreted in this way, that if you try to apply forces based on, let's say, the first mode of vibration, you are only going to cause displacements on the first mode of vibration. Or in other words, the work done by one mode into another mode is always 0. So after all this theory, we can calculate these matrices highlighted in blue. So if we do phi transpose M phi, we're going to get this matrix here, 4.59, 0, 0, 866. And if we do the same with the K matrix, we get 13,000 and then 119,000. And also we get 0, 0 in these two terms. So what's interesting about these particular matrices is that both of them are diagonal matrices, which means the terms outside of the diagonal are equal to 0. Now, why is this critical? Why is this very, very important? And to this, I want to look back into the equations from the first video in the coupled form. And I told you, what is causing the fact that this is coupled? Is this minus k2x2, and in this equation is this minus k2x1. And where does these two come from? They come from this term here on the stiffness matrix and this term here in the stiffness matrix. So it's the fact that the stiffness matrix is not diagonal that causes your dynamic equations of equilibrium to be coupled. It is this minus k2 that is messing up this equation. If we didn't have this k2x2, we had an equation just for x1, so we knew how to solve it. And if we didn't have this minus k2x1 here, we could solve this one for x2. So it's these terms that are messing up our calculations. So now that we figured out a way to obtain both matrices being diagonal, so phi transpose M phi would just be M1, 0, 0, M2. And we have names for this. M1 is what we call the generalized mass of mode 1, and M2 is what we call the generalized mass of mode 2. And now the same applies for the stiffness matrix. So this K1 is the generalized stiffness of mode 1, and this is the generalized stiffness of mode 2. Don't confuse with this K1 and K2, which have a more physical meaning related to the columns. So we use small letters for the initial stiffness matrix, and then we use capital letters for the modal stiffness matrix. So to finalize our problem, we now know that these two matrices are diagonal, and if we write this top equation with these two matrices, we are just substituting this by this, and that's that. And we're substituting this K matrix by this bit here, right? We're substituting this. So if we try to write this equation that is in the matrix form, if we try to write it as a system of equations, and we substitute right away the accelerations by minus omega squared times the displacement, we get this equation on the top and this equation on the bottom. So 459 times y1 of t times the modal circular natural frequency. So this minus omega 1 is the same omega 1 that we learned how to calculate in the second video. So the modal circular natural frequency of mode 1. And this plus this number times y1 equals to 0. So now you can see that this equation only depends on y1. And the second equation, the same thing. It's just this modal mass times y2 and also timed by the modal circular natural frequency of mode 2 plus the modal stiffness times y2. If we have two equations, both of them depending only in one variable, then we can solve them as single degree of freedom. And we can now finally solve our system. And at the end, we can just recombine it using the modal superposition that we discussed in the beginning. So in summary, from all of these videos that we've been discussing, we started by introducing the dynamic equations of equilibrium just based on equilibrium of the masses. And we understood that we can't solve it because the motions of the masses are coupled. And we started talking about modal circular natural frequencies and using this equation to find those properties. On the third video, we discussed how to get the mode shapes from this equation and knowing the modal circular natural frequencies. But what we discussed today, and probably philosophically the most important concepts to have, is this idea of modal analysis, that the displacements of our masses x can be decomposed by the mode shapes times the modal displacements y. The modal matrix is just the vectors written as columns. Modal stiffnesses are obtained by phi transpose k phi, and modal masses are phi transpose m phi. And we finally cracked the code for this problem, because when we write it in such a way, we get dynamic equations of equilibrium in an uncoupled form. So we have one equation for each mode of vibration, which we can solve as a single degree of freedom. And by the way, very important that at the end, to recombine to find the displacements of your masses, once you know all your y1s, y2s, and all the modes that you might have, you just multiply by the modal matrix again, and you get the displacements of your degrees of freedom. So I hope you enjoyed this series. Thank you for watching, and have a good day.